What's up, everybody? We're back at it again with Physics 207. We're going to be doing the 2017 exam today. I did a little bit of this earlier, so it's not too bad, but there are some confusing bits that I thought would be good to do in a video. Yeah, let's get right into it. So we got some laws or concepts to look at here, first and foremost. Yeah, so all these will be probably important later, but some that I would add, just like J equals current over cross-sectional area. Let's see, what's another one we can think of? I don't know, the volume of a sphere might be useful. The volume of a cylinder. What was that? Pi r squared L. Yeah. So, let us jump right up to it. So, first question, we got a circuit problem. Now, these are usually not too bad, and they should be like the gimme problems on these exams most of the time. So, what the law we're probably going to be using here is just I times R. And then also like Kirchhoff's laws, or the junction law, where it's like, V minus IR equals 0, or, the currents add up to each other. I guess you could also just do I. So let us get this going. Okay, so this question, this current, or this circuit is going to go like this. So how I usually do these is that, well, we can see that all the R's are the same. All the resistors have the same resistance. We have two different capacitors, so two different capacitances, capaciti, whatever you would say. And so then we have two different batteries, and we know all these values. So we need to use those to solve for the currents and the charges on the capacitors. Also, another good one to use is that charge divided by C equals V, which is a good one as well. I'll put this over here. So, let us bust this out, right? Okay, so let's start with our first current. We got a current going from battery 1 here. It's going to go over resistor 1, and it's going to enter this junction. So we know that this circuit is in steady state because the circuit was put together a long time ago. That's usually what that means. So steady state. Steady state capacitor, steady state circuit, which means that the capacitors should be fully charged. And now when the capacitors are fully charged, that means that current can't flow across the part of the wire that the capacitor's on, or the circuit the capacitor's on. So when the current one enters this junction here, it's not going to go down. It's only going to go up towards this next resistor. So we can just label this. And since it's not splitting off at this junction to go to the capacitor, it'll have the same value as the current coming from the battery. And then again, it'll enter this junction or come together at this junction, theoretically. But since the capacitor's there's not going to be anything coming, and so the current's just going to keep flowing. Same current. And then it's going to round this corner. And again, this battery here isn't going to be, it's going to be producing a current, but there will not be a current since it's in steady state. So there's just still the same current that we have from this battery right here. So the current is flowing and over this resistor, and it's going to go up to this junction, and it'll just continue being the same current, and then it'll just come back up again. There we go. Okay. Now, another thing I like to add is the electric field lines, or just the direction that the electrons would be flowing. over the batteries and capacitors. Now, electrons flow opposite of current most of the time. There are some instances where they wouldn't, but yeah, usually you just want to go draw an arrow from positive to negative, and this will help later when we start doing our loops. So capacitor 1 is going to be building up charges, positive charges on this side of it, because if you imagine that when the circuit was put together, the current would be flowing from here, and it would be going towards the capacitor. And so it'd be charging this side of it with the negative charges, and then the positive charges, and then the negative charges would be on the other side. Then same thing here. This one's a little more obvious to see. This plate would be positive, and this plate would be negative, because it's same size as the battery here. Okay, cool. So that means we can draw our arrows. Right? So there we go. All right. So what we want to do first is draw our loops. So what I would probably do here, since we have this kind of weird shape in the middle, wouldn't be really helpful to draw a loop there, but I would draw a loop here, a loop here, and a loop going all the way around the outside. Sorry, that was bad. A loop going all the way around the outside of the circuit. There we go. So, there we go. So, we'll call this loop 1, loop 2, and loop 3. All right, so loop 1 is going to go this way, right? So we're flowing over resistor 1, which has capacitor 1. But actually, let's start with the battery. So we're going this way, right, with the loop. So it's going over the battery, so it's going against the electric field. So that's voltage 1. Then we're going across this first resistor, and then we're going across another resistor, and then we go over another one down here, and then we come right back to where we started, and all that added together and subtracted should be 0. Cool. Okay, so then what we want to do is want to do loop 2. So loop 2 is going all the way around this way. So it's going to be going along that first resistor there. This one in there. And then it's going to be going against the capacitor. So we'll have charge 1 divided by capacitance 1. And that's going to be equal to 0. Then we have loop 3. So we have negative C2, or charge 2 over C2 plus, or we could do actually plus V2 plus IR. That equals 0. So we want to find the current and the charge on each capacitor. So we'll solve this first one for current. So if you add V1 over and then take out R, there's 3 of them, so it's V1 over 3R. Then we can solve this one for charge 1, which would be C1 times I times R, which equals charge. And then you can solve this one for the same thing. We can actually plug I in for this one and make it a little bit easier. Just get rid of one of our R's, or R. So we'd have C2 times V2 plus C2 IR. But you could also just say V1 over 3. Because if you plug in VI here into this I, the R will cancel out. And then that will equal charge 2. Cool. So that's the first question there. All right, not too bad. Obviously we need to plug these in to these equations, but, not too bad, not too shabby. All right, let's move on to the next question. Okay, so, and then here you just, you literally just plug in the numbers. I'm not going to do that, though, because I don't really want to. But, you would just do that. So, in the circuit below, all the R's, V's are known. The circuit was put together a long time ago. So, again, this one's in steady state. Steady. Oh, my Lord. I can't spell today, guys. Okay, so steady. Did it again. Steady state. Find the currents in each resistor. You must clearly indicate what you're doing or you'll receive no credit. Okay, so we got our first battery here. It's going to be giving off a current. We'll call that current 1. Then it'll split at this junction into I2 or I3, or let's say I2 and I3. Now, something interesting is going to happen here whenever these split, but we will get to that in a second. What I would recommend doing for a lot of these like current problems is just drawing where you think the currents would be, no matter what, and then let the math show you. Except that there's like a capacitor, of course. Like, don't draw a current going towards a capacitor, but yeah. Anyway, and another interesting thing about these questions too is like a lot of current usually flows from the positive end of a battery, right? Now, in this question, we have that current is flowing towards current 1 here. When it comes back together from current 3 and 2 at this junction here that I'm drawing, comes current 1 again. And then it goes towards the positive end of battery 2. That feels a little counterintuitive, but that is a possibility, especially in this sort of problem. And that has to do with, where the junctions are, how the circuits are oriented, the voltage of the batteries. This battery might have a higher voltage than this battery. We don't know. The math will tell us that, though. So that's what we would need to remember most of the time with these questions. Is that just do what you feel like is intuitive, and then let the math kind of tell you what is the sign of these values. Because that'll tell you if there's even a current to begin with or what direction it's going in. Because it could very, very well be that this battery 2 is pushing up the current along the circuit, and all these signs would be flipped, or all these arrows would be flipped. So someone asked me that question, and it really made me think, because I wasn't actually sure about that either until they asked. So, great question. And it really just has to do with the fact that the voltages could be different, the resistances could be different. But really do what's best for you, draw the currents in the direction you want, and then go from there. Set up your equations, set up your lines, and then that will tell you what direction the current's in, or if there even is a current where you drew one to be. So that was a great little thing to kind of remember, just because we can get in a rhythm here. But anyway, okay, so again, same laws we're going to be using here. V equals IR. We have no capacitors, so we don't need capacitance. But let's get going. Okay, so we've got one big loop going in the center here, and we've got one loop here. So, one thing we didn't have to do in the last question is identify what currents add together to make another one. So one of the first things I would write down here is that I1 equals I2 plus I3, right? So, but that might not be that is the case, but there might not be a current. And we'll see that as we go into this question. So loop one is going to be, remember, let's draw our electric field lines here. Also, I feel like it may not be electric field lines, but just the direction the electrons are going. So we got negative voltage 1 plus I1R1 plus I3R2 plus I1R3 plus voltage 2 plus current 1, resistance 4. And that's going to equal 0. Okay, so we want to work with this one real quick because it is a mess, right? So let's put the voltages near each other, and let's put all the resistances that have current 1, like could just combine like terms, right? So we have current 1, R1. Oh. Let's see here. I had to do this one earlier because it was actually kind of confusing at first. Oh, I accidentally wrote current 4. That's why I'm confused. Okay, so plus current 1 times R3 plus current 1 R4, right? Yeah, and then we'll have just one thing with current 3 going through it. That'll equal 0. Okay. Now, what we can do here is we can have voltage 1 plus voltage 2 plus I1 times R1 plus R3 plus R4 plus I3 R2. So there we go. That's the most we can do with it right now. But as you can see, it's kind of hard to solve for either of these currents with just one equation. So let's look at loop 2. Loop 2 is going to have, since there would be a loop here, right? The only thing that we have doing anything is negative I3 times R3 equals 0. Now, what we can tell here immediately is that this might not make the most sense, but when you consider the fact that resistance 3 is an intrinsic value to the capacitor, or sorry, resistance 2. Sorry, did I do that correctly? Yeah, I did. Okay, so resistance 2 right here is a intrinsic property of the circuit. It's like it is a, it's kind of like how, like an object has mass. It can't have 0 mass. If this is a resistor, it can't have 0 resistance, if you think about it. But what you can have is 0 current. So, as I was mentioning, when you're doing these problems, you can write all the currents out that you want, except, like capacitors and stuff. And then you kind of just set up these loop equations, and as you do the math, you'll see that things can cancel out or go to 0. And that's what's going on here. So I3 equals 0 because resistance 3 cannot equal 0. So, resistance 2 can't equal 0. So out of the two of them, current 3 would have to be 0. Which means that this current equation is I1 equals I2. And then you could just say that I equals I1, which equals I2. All right, so then we can take this equation here and plug in for I and set I3 equal to 0. So we're changing I1 to I, which I guess you don't have to, but I feel like it's easier to see what's happening here. And then obviously that would be 0 because I3 would cancel that out. And then you can just solve for current, which would end up just being V1 minus V2 over R1 plus R3 plus R4. All right. So there we go. That is our answer. And I guess you could also just add in that I1 equals I2 and I3 equals 0, since we are trying to find the currents in each resistor. Okay, cool. Now, next question. This is gonna be a little bit of a long one, but it's a pretty good conceptual question, I would say, just kind of like for Gauss's law. So this is a Gauss's law question. So a negative charge, negative Q, is uniformly spread in a spherical shell with an inner radius A and an outer radius 3A. Find the difference in electric potential between the center of the shell and a point 2A away from the center. So, some concepts we want to use here is, I immediately think, we have, Gauss's law. That's one we're going to want to use. Electric potential difference. Then another one I think would be useful here is the fact that rho, which is charge density, equals charge over volume. We're also going to probably want the volume of a sphere. That might be helpful eventually. And then we're probably also going to need... No, that should actually be it. Okay, so let's think about this. So our first step is we want to make a Gaussian surface that encapsulates the charge, or encapsulates the electric field. So this charge negative Q is distributed all around here. It's a inducting sphere, right? So that's usually implied. If it was a conducting sphere, the charge would be on the surface of either here or here. But it's an inducting sphere, so it's universally spread across. So that's why we have charge density for this question. So, let's see here. Our first step would be to get an equation for the electric field. Sorry, I had a really large burrito bowl at the one and only Copperhead Jack's about an hour ago, so I'm slowing down. But let's see here. So, Gauss's law. An oversimplification we can say is that the electric field, well, not really an oversimplification, but just something that we know, and we can just, assume, is that the electric field is constant on this thing. So we can take E out of the integral, which leaves us with the surface integral, ds, which would then leave, so now we got to think about what do we want our Gaussian surface to be, right? So we know that this is, a spherical shell, right? So what we probably want is more spherical shells to encapsulate this electric field, or the charge. And so we would evaluate this integral here as the surface area of a sphere. So E times 4 pi r squared is the surface area of a sphere. And if you ever forget what the surface area of a sphere is, you can just take the derivative of volume with respect to the radius, which would just be 4 pi r squared dr. And this will actually be helpful soon as well. That's really ugly too, guys. Okay, so now what we want to do is set this equal to Q enclosed epsilon naught. And then we'll just solve for the electric field. And don't forget your vector there. 4 pi r squared times epsilon naught in the radial direction. Cool. Now what we want to do is find what this is. Because yes, we know that the charge is negative Q, but we don't know what the Q enclosed is. And that's going to be important for taking the electric potential difference. Because as we have it now, we don't really know what the electric field even is because we don't have a value for the charge enclosed. So now what we want to do is find the electric field at differing points, or different radiuses, or radii. So a great place to start is, r less than a. When the radius of the Gaussian sphere, the Gaussian object that we're taking, if we're taking concentric spherical shapes with increasing radii from the center, good place to start is 0. So I'll write that in here actually. So between 0 and a, when the radius is between 0 and a, there is going to be no charge because the charge starts at a. So Q enclosed is 0. There is no charge if the Gaussian object was in this region, it would be enclosing no charge because the charge starts at A, which means that the electric field here is similarly 0. Because if you plug this charge into the equation, you get 0. Now, the nice thing about this question is we were trying to find the electric potential difference between A and 2A, which is or 0 and 2A. See the center of the shell and 2A from the center. As you can tell, and because the sphere itself is a radius of 3A, like in total, we're integrating or finding the electric potential between 0, radius equals 0, and radius equals 2A, which is some inner part of the sphere. So what that means for us is that we really only have to find the Gaussian surface, or find the Q enclosed, charge enclosed between A, radius A, and radius 3A. So, this part of the sphere. All right, so how we're going to do that is we have A less than R less than 3A. Okay. And so Q enclosed is going to be the integral of rho 4 pi r times 4 pi r squared. Now, where I got this from is the fact that, so we have it here, that rho equals Q over V. But this can also be written as charge equals rho times V. Now, that's the linear form of this concept. But since we are integrating over a region, we need to integrate over volumes. So that doesn't make the most sense in the world. But we're accumulating charge as we move away from radius A to 3A. Because we're growing. It's growing. The Gaussian surface is growing in radius as you go from A to 3A. So we're essentially saying this, honestly. Or, sorry, 4 pi r squared, because the integral of 4 pi r squared dr is the volume of a sphere, which is what we're ultimately trying to find, because charge equals rho times V. But that can also just be rho times dr, or integral of dr. It's kind of hard to explain, but the fact of the matter is that we're still using this concept here, but we're just integrating along the Gaussian, we're accumulating the Gaussian surfaces. Like if you were to like an onion has layers, we're accumulating layers of said onion as it encapsulates more of the onion. I don't know if that helps, but let's keep going. So that's what we're doing here. And so what we want to do is integrate this from where the charge starts, which is A, and we want to just go to R, because we want this to be this is going to be a function of R, because the Q enclosed is going to depend entirely on where this Gaussian object is, or how large it is, or what its radius is. So anyway, let us integrate this. So rho can come out because rho is a constant value, because we were told it's uniformly spread, which means that rho is a constant. Unless stated otherwise, it usually is. So rho can come out, and we know rho is going to end up just being negative Q over 4/3 pi times the radius. Now, another thing to kind of keep in mind here is that rho, being a constant value, only applies to this part of the object, because it's the only part of the object that has charge. So rho is going to be the charge, which is negative, a negative Q, divided by the volume of this object, which we know the volume of a sphere is 4/3 pi r cubed, and our radius is 3A minus A. So we'll end up having 3 cubed minus a cubed, which will equal negative q thirds pi times 26a cubed, which we can then evaluate to just be negative 3q, because the 3 can go up, times over 4 times pi times 26 times a cubed, which would just be 104 pi a cubed. All right, so that's what we end up having for rho. So rho can end up just coming out being negative 3q over 104 pi a cubed. And then, as we know, when we evaluate the integral that's left, which is 4 pi r squared, we'll end up having 4 thirds pi times radius cubed, which we're evaluating the radius from a to r. So we would have r cubed minus a cubed. Correct. So now what we want to do is we can cancel out the 3, we can cancel out the pi, and we cancel out this 104 at the bottom here. So what we end up getting is negative q over 26 a cubed times r cubed minus a cubed. Now, there we go. So now we want to plug this q enclosed into the electric field equation that we have, so we can get electric field 2 here. And we'll end up having that it will equal so we'll end up having negative q r cubed minus a cubed over 26 a cubed, right? Then we'll have 4 pi r squared epsilon naught. So we're just plugging it into this equation here. That will end up being negative q r cubed plus q a cubed over 104 pi r squared a squared epsilon naught IR. So quite horrendous, as you can see. And so there you go. Now, what we would like to do is add these two electric fields together. But as you can see, we only have one electric field, really, right? Because the other one's 0. So next what we want to do is integrate this in the electric potential difference equation. So if we take this here, oh, the iPad's freezing. So here's our equation for that, correct? So we'll have, and remember we're doing it from 2a, or 0 to 2a. Now, we know this is the negative integral of the electric field. I'm going to speed run through this because this is just calculus, and I do have to do something in like 17 minutes. So I'm going to speed run this. But the last physics kind of concept we need to understand to finish this problem out is to know that the electric potential difference from 0 to 2a is really just a to 2a, right? It's the same thing because remember, like I said, the object that has charge starts at the radius equals a, and it ends at radius 3a, which means that there is no charge prior to a, so radius less than a, as we saw here, which means that there will be no effect on the electric potential difference when the radius is less than a. So we can adjust this integral to just say we're doing the electric potential difference between a and 2a. Okay, and if we want to plug this in, what we would probably want to do is split up this equation for the electric field in the top bottom, since they both have, since the radius is in the denominator, and that's the variable that we're integrating over, or integrating with respect to. And so what we would probably end up having here is a to 2a of q, and the radiuses would cancel. If you split this in half, radius would cancel, or the radius would cancel out, and you'd just leave you with 1 on the top. You'd have 104 pi a squared epsilon naught dr minus a to 2a of the same thing. So we'd have q a cubed, which is constant, over 104 pi r squared epsilon naught dr. Cool. So then from that point forward, you would just have to, integrate it with, like you could rip all this stuff out right here as a constant. This would also be a constant. And so you'd just be taking r squared, 1 over r squared integral, and then the r integral from a to 2a. And that should get you your answer. Sorry I can't do it right now, but this is just calculus. I'm sure we kind of know how to do that. But physical concepts, all there. Hopefully that was helpful. Okay, so I might have to run this one as well. But so this next question here, we have a cylindrical shell made of material with a constant resistivity P1, or rho 1. The shell has inner radius A and outer radius B. It is surrounded by another cylindrical shell with an inner radius B and outer radius F. The constant resistivity P2, or rho 2, sorry. A battery with known voltage V, that's nice, is connected as shown so that a constant current is made to flow radially out from the inner surface to the outer. The length of the cylindrical shell is W. Find the current. Okay. Let me just hold on a second. Let me check my answers real quick. One sec. I just got to find where I did this one so I can check my answers as we do this one. Okay. All right, so what we want to use in this question is we want to find the current, right? So that automatically tells me that we're using the this equation for current here. There's the one we're given. We're probably also using a resistance equation, which we're also given. Let me make sure that that's the right one. Yeah. Okay, and then all right, so let's try and run through this real quick. So first step is we want to do the inner sphere thing. So the area of that would be 2 pi r w. And then we want to use that in the resistance formula. And this is the same A, by the way. Cross-sectional area. All right, so resistance 1 is going to equal the integral of resistance 1, or resistivity 1, so rho, times 1 over area with respect to dr. Now, where the heck did I get this from? All we're really doing, again, like we did with resistance and the resistivity in the last question, or a Q enclosed, like when we were trying to integrate it, we're basically just saying that dr, so the derivative of resistance, equals rho times the integral of dr A. And now we're doing cylinders and not lines, so that L is just going to be the radius instead. So we can evaluate this. And we want to evaluate this from the inner one, because we have inner radius A and outer radius B. So we're going to be doing that from A to B. One thing to remember for resistance is that when you're integrating it, you want to integrate it over the entire object. You don't want to integrate over a specific region, because resistance, again, is a value is an intrinsic property of the entire material, the entire object. Right. Trying to think of an example, but I don't know. Just remember, resistance is an intrinsic value of an object, and you want to integrate over that entire object's length or radius. And since we have voltage going from the inside to the outside object of the object, we want to integrate along a radial. We want to integrate radially, or along we want to integrate with respect to radius, because we want to grow out from the center with different cylinders. Right. So then what we want to do is just integrate this. And that would be rho 1 times 1 over 2 pi w times, and since we're doing 1 over r, that's going to become ln b over a. Correct? But also that could just be written as ln b minus ln a. Correct. So, which, again, equivalently is ln b over a. Cool. Then what we want to do is we're going to do the outer cylinder. Same thing. It's got the same area. It's entirely dependent on the radius, of course, but it's the same formula for area. So then we have resistance 2, which equals the integral of rho 2 1 over 2 pi WR, which is area, times dot dr. And then we want to do that from its radius, its inner radius to its outer radius, so B to F. And then again, same sort of equation here would result, so we get 2 pi W times ln F over B. Cool. So now we can just add these resistances together to get the main resistance, or the total resistance. So R total equals resistance 1 plus resistance 2, which is just going to be rho 1 2 pi W ln B over A plus rho 2 2 pi W ln F over B. Bam! Boom shakalaka. Okay, so then literally all we have to do now is to find current. We need to use this equation. And what's nice is that we know what voltage is because we were told that there's a battery with voltage V. So we literally just do I equals voltage over this, R total. So that's going to be rho 1 over 2 pi W ln B over A plus rho 2 2 pi W ln F over B. And then that is literally all we have to do. And that's the answer. Of course, you could flip it up here. So 2 pi W times V over rho 1 ln B over A plus rho 2 ln of F over B. All right, cool. Well, guys, sorry to speed that up, but that is really all you have to do for these last two questions. Some of these are actually not too bad, but hopefully that was helpful. I'm going to try and do another one of these exams tonight before tomorrow, since the exam's tomorrow. So hopefully these were helpful. I know the exam's literally tomorrow, but maybe this will help someone in the future. I don't know. But, okay, yeah, so that's it with me. If you have any questions, of course, drop a comment. I might answer it. Who knows? But yeah, so good luck on the exam if you're taking it or whatever. But I'll see y'all later.